Hi, everyone. Thanks for joining us today. So welcome to our 74th session of the MedAI Group Exchange. This week, we have three speakers, Arjun, Karan, and Sabri from Stanford here with us to speak about Meerkat, interactive data systems for unstructured data and foundation models. Arjun is a fourth-year EE PhD student, work with Akshay Chowdhury and Chris Ray. He's interested in how signal processing principles can improve robustness, efficiency, and scalability in machine learning. He's excited about how these methods can help build scalable deployment and validation systems for challenging applications in healthcare and the sciences. Karan is a fifth-year CS PhD student at Stanford, advised by Chris Ray. He's interested in sequence modeling techniques for building large-scale foundation models, as well as problems that arise due to the deployment of machine learning models to practice. As part of the Meerkat project, he thinks about how the application of foundation models will change systems for data science and engineering. He's a recipient of the CBEL Foundation Scholarship. Sabri is a third-year PhD student advised by Chris Ray and James Zhou. He is broadly interested in how we can bring machine learning to bear in challenging applied settings like medicine and the sciences. To this end, he has recently been working on data management tools that help practitioners better understand their data. He is supported by the National Science Foundation Graduate Research Fellowship. This is the second time for Arjun and Sabri to speak at MedAI, so welcome back. We also welcome Karan for the first time at MedAI. Before we start, could you tell us your preference on when you want to take questions?
We can take them as we're talking.
Sounds good. So without further ado, let me hand it over to the speakers.
Great. Thanks so much, C, and thanks for inviting us back and kind of here to talk about Meerkat. So I think what we're really interested in talking about today is not just Meerkat as a tool, but really how it can be applied in medicine, in particular in medical AI, and really focusing on this idea of how do we think about interdisciplinary collaboration, which we often have to do with a lot of the domain experts in our field, and really bring machine learning to them and have their expertise easily kind of come down to us. So just to outline the talk a little bit, we'll start by thinking about, well, what does interdisciplinary ML really look like? So in medicine, we often interact with these domain experts, and how can we really kind of dive into what those interactions can really be? And then what we'll kind of move on to is think about, well, what are some challenges that we face in order to making this collaboration very seamless? And I think a lot of us know that it's very hard to kind of create that pipeline of talking with clinicians, not because we don't want to, but because it's more there are challenges in terms of the infrastructure that we have for being able to communicate. We'll then kind of dive into talking about Meerkat, which is a tool that we've built for wrangling and understanding unstructured data, and really bringing machine learning tools to these interactive systems. And we'll really dive into focusing on particular case studies of things like model debugging, which we often do in the medical field, of figuring out things like where are models failing, so inspecting where the errors are, discovering what these errors are as well in terms of kind of being able to characterize them, and of course, refining our data so that we can improve our models down the line. And we'll conclude with some takeaways. So when we think about machine learning, we often think purely about this kind of model engineering kind of stack, but it's really much broader than that, especially in the applied domains like medicine. So we have to often think about, well, how will we collect our data? Who's going to annotate it? And what are the particular sets of tasks that we want to tackle? We also need to think about when we're building our model, how should we keep iterating over our data? So how do we do things like refine our data, and how do we refine our tasks for the particular specifications that we're interested in? And of course, we need to think about things like evaluation and deployment in the wild, where we should be able to track kind of the performance of these models and be able to kind of reassess how we should change our models and versions moving forward. So this is all great because these are kind of critical parts of the applied machine learning pipeline, but all of these parts require interaction with domain experts, because these are the folks that know how machine learning can actually impact downstream clinical outcomes in practice, and how we should actually be thinking about collecting our data and providing our annotations. So really, when we're thinking about all three of these steps, we're thinking about how is the data being kind of manifested and kind of sent between the engineering stack as well as these domain experts. And so when we're thinking about kind of simplifying this pipeline, we really have to think about data as being the universal language for facilitating these interdisciplinary collaborations. So kind of if we dive into one of these case studies that we often kind of see in the medical setting, things like medical image classification, we may be quite familiar with kind of two main steps, which are A, collecting the data and the labels, which are often done with the help of these domain experts, and then B, kind of training our models and then evaluating them and kind of if they achieve state-of-the-art results, kind of going on and publishing them. But in practice, what we often have to kind of think about as well is, well, how do we improve these models continuously? So we have to think about things like, well, where are our errors actually coming from? So we need to do things like inspect our data and inspect our errors. We also need to do things like characterizing how our errors are being manifested. So what do our errors look like? Are there particular images where we are failing on? And of course, we can use all of this information to further refine our data. So we can collect more labels, collect more images, and really repeat this pipeline again so that we can end up with a better model. And it's important to note here that this is cyclical, right? So the models are continuously improving, and we want to be able to have the infrastructure for being able to facilitate these interactions. And at its core, this entire debugging step really requires close ties and interaction with domain experts. And so the natural question to ask is, well, what are the challenges that we often face in this collaboration effort? So the first is that the data that we're often trying to wrangle or look over is quite large. So when we're thinking about medical imaging, when we're thinking about the large sets of data sets that are out there, it's kind of pretty difficult to manually go through our data and inspect where all of these errors are occurring, or being able to kind of characterize or find some attributes about these data kind of at an aggregate scale. The second kind of big advantage of medicine is that the data that we often collect is multimodal, but this can be quite challenging because now we have to extract attributes out of this kind of multimodal, often unstructured data. And this can be quite challenging. So this is often why we build a lot of our ML tools, but we often can't kind of predict how well our ML tools can be. And kind of with the push towards foundation models, which are kind of these kind of catch-all models for kind of performing a lot of these analyses or extracting attributes of interest, we want to make sure that we can use them, but be able to use them safely. And of course, kind of one of the biggest parts is that collecting data is quite difficult. So whether this is related to collecting the data itself in terms of the images or the EEGs or other kinds of patient-specific data, but also the labels, which require kind of expert annotations in order to be considered ground truth and really help refine our model. And if we can't create good infrastructure for collecting this information back from domain experts, it's very difficult to keep iterating on our model and really be able to facilitate this interdisciplinary collaboration at scale.
Awesome. So I'm going to take over here, Arjun. I guess you can just kind of move forward on the slides when it seems like it's appropriate. Awesome. So what I want to do is I want to think a little bit about how Meerkat can help solve some of these challenges that Arjun just brought up. And in particular, I'm going to describe how Meerkat can facilitate communication between machine learning engineers and domain experts by providing this common platform through which both parties can interact with a shared data source. So on the engineering side, we might have some data scientists, machine learning researchers who want to use tools that are familiar to them. And in Meerkat, the tools, or like the interface for the engineering side, are centered on data frames. So data frames like what you might interact with in pandas or in R, and other common programming abstractions that should be familiar to a data scientist. So on the engineering side, they're using code to interact with data. And then on the clinical side, domain experts can actually visualize the data and, more importantly, provide feedback on the data via labeling and other interaction. And so what we have is this system where both sides of the collaboration can kind of communicate and interact with the shared data source using the interface that kind of makes most sense and is most efficient for them. So I'm going to step through an example, the example that Arjun brought up earlier about how we can debug these image classification models. And at each stage in this pipeline, from data inspection, error discovery to data refinement, we'll talk about and show explicit examples of how Meerkat can kind of help us do this process and facilitate that communication between both sides of the collaboration. So let's dive in. So we can start with kind of error inspection and data inspection. So let's imagine that we just trained a machine learning model. It's trained to classify pneumothorax in this case. And the data science just wrapped up. They computed the AUROC. They found that the model has a pretty good AUROC of like 91%, feeling pretty good. But they want to do a little bit better, and they certainly want to ensure that there aren't any failure modes that might pop up in practice that they should know about before deployment. So they start engaging with the other side of the collaboration, the clinicians, to see if they can kind of understand where the model might be performing well and where the model might be performing poorly. So using Meerkat, what the data scientists can do is they can use the data frame API to load in all of the validation examples from a CSV, kind of represent the DICOM files that are pointed to by that CSV as a new column in the data frame, and then create a gallery type view that visualizes those images and every single example. Then they can send over a link to the clinician or whoever else is on their team that has a better understanding of the actual images being explored. They can send over that link. The clinician can then open it up and go through and actually explore the data. So what we're doing here in this video is we're actually going through and just kind of setting filters to identify cases where the prediction does not align with what the ground truth label is. And we can kind of click in, zoom in on a particular example, and actually look and see kind of where the mistakes are being made and what those examples look like. So
may I ask a question here?
Yeah, definitely.
Yeah, I think this is super cool and very useful. I wonder if this can actually handle PHI data.
Yeah, that's a great question. So there are certainly concerns about how to handle PHI, and I don't want to make any promises because I'm not an expert in terms of security. That being said, this is something that we've considered a lot. And I think one of the things that we have prioritized a ton, which has been sort of grounded in our experience working with medical data, is we wanted to make sure that whatever solution we had worked without it requiring that the data leave the premise where it is residing. So say there's like a lab server or there's an area on like a cryptid server that is safe for PHI. We don't want to have to take that data and upload it to the cloud or upload it to some other repository. So what's going on here is the quote unquote server that is serving this user interface, that's running on the same machine where the data scientists would otherwise be doing their analyses. And then when they kind of create this shareable link, the clinician is actually effectively connecting directly into that machine where the data lives kind of securely. Now, that being said, I think there's still more work for us to do in terms of really ensuring that that connection is secure, and you know, there's more work to be doing on that front. But this is kind of been top of mind for us, and it's really important that the data doesn't have to leave that one spot where it currently is living. Does that make sense?
Yeah, sounds good. I'm glad that you are actually thinking about this and taking actions to deal with PHI data.
Yeah, totally. It's super important. And I feel like in the past, it's been a pain point for me when I was working with medical data, where I wanted to use certain tools for visualizing data, but it did require kind of pushing stuff up to the cloud, which of course wasn't okay. So excited to kind of work with folks and figure out what a good workflow here would look like. Okay, cool. So go to the next slide. We can also play this video. So say the doctor comes back to the data scientist and says, hey, this is great, but there aren't really that many structured fields for me to explore, right? Basically, I have a column in my data frame for whether or not the person is pneumothorax. I have another column in the data frame for the prediction, but that's kind of it. The image, though, has all of this rich information in it that isn't being communicated through the structured fields. So the clinician says, is there another way that we can maybe explore that? So the data scientist goes back to their code, and what they do is they write a little script, you know, maybe like, I think this is maybe 15 lines of Meerkat code that creates a scatter plot of UMAP embeddings of all of the different DICOM images and puts them alongside the gallery that we were looking at before. And what this does is it allows the clinician to explore and try to find semantically meaningful groups where the model might be performing poorly. So let's take a look at this scatter plot. It's a little bit blurry here maybe, but you can see that the points are colored kind of orange and blue, depending on whether or not the model was correct. One thing that jumps out to me is that there isn't any clear cluster where the orange and the blue are like clustering, right? There isn't like one cluster where all the orange dots are. So while there are some interesting clusters, like I was playing around with this interface earlier, and I noticed that one cluster, had certain characteristics, like all of the images were a little bit blurry. There isn't a clear cluster where all the errors are happening. So maybe as a next step, the clinician can kind of explore here, get some ideas about what the error might be. They're going to go back to the clinician and say, or sorry, go back to the data scientists and say, can we try to discover more situations in which the model is making errors explicitly? So Arjun can go to the next slide. So to do that, what we're going to use is some features inside of Meerkat that are explicitly designed for trying to identify subgroups of data where the model is performing poorly. To do this, we're going to be using some slice discovery algorithms. I was actually, last time I was on the MedAI, I gave a presentation here. I chatted about some slice discovery algorithms. So here we're using one of those to try to identify groups of data where the model might be performing poorly. On the left, the data scientist has sort of created this little bar chart showing the difference in performance, the difference in AUROC on different slices. And on the right, again, we're just showing the images in each of those slices. So when, here, let's, once it goes back to the, yeah, perfect. So yeah, so when the clinician clicks on one of the bars, they can actually explore and look at the examples in that slice. What's interesting here is that on one of the slices, the one where the AUROC, I believe, is like closer to 0.73, well below what the global AUROC of 0.91 is, when they click on that slice, they find actually that a lot of the examples have pacemakers and chest tubes, right? So this is kind of interesting. There's a large degradation in performance, almost 20 points in AUROC on images with certain characteristics. So the clinician might come up with like this hypothesis that says, okay, hey, our model's pretty good overall, 91%, but maybe there's some concerns that it's not really doing very well on particular subgroups. So the next question is, well, we'd like to have a very precise estimate of how well does the model do on patients, say, with chest tubes, but no pneumothorax, and without chest tubes and pneumothorax. In other words, harder cases where there isn't this spurious correlation. One thing that's been observed sometimes in the literature is that machine learning models trained to do clinical classification tasks will kind of latch on to these correlations between artifacts in the images, like whether or not someone's wearing whether or not someone has a chest tube, to make its predictions. We might be suspicious here after looking at some of these discovered slices that this might be happening. But in order to get a good estimate and know for sure that this is happening, we actually need to do some labeling. Like we want to be able to label all of the examples in the data set where folks have chest tubes so that we can compute the statistic of what is the error rate among folks with chest tubes and no pneumothorax compared to the error rate among folks with pneumothorax and a chest tube. Let me pause there because that was probably a lot to take in. Any questions?
Yeah, I had a question actually, Sabri.
Yeah.
Yeah, this is amazing work. So I actually wanted to go back to the UMAP representations that you had. Yeah. So while like it's a very natural step to actually embed your images directly into UMAP, is there a way where, I mean, you've trained this model, so the model embeddings are actually going to be a better way of getting those UMAP embeddings? And so I was thinking if there's like a three-way thing where you have your image, you have the corresponding representations that you gain from your model, and then the projection of that into a UMAP. And so I'm guessing that the model, if it has 0.91 AUROC, the clusters are going to be much better in that UMAP. And would you be able to do something with Meerkat to kind of identify those clusters?
Yeah, that's a great question. So I think one high-level point to make here, and I think this is why I really appreciate you asking this question, is because Meerkat is a relatively low-level programming language for the data scientist, it more resembles like Seaborn or like Matplotlib in terms of its controllability. And what that means is, yeah, you could use any embedding you want or any X or Y axis that you want in the scatter plot to do your explorations. Here we did UMAP just because, I don't know, it was just like the first thing that I thought of when I was making the demo, but you could do anything else. And in fact, to be honest, personally, I actually prefer using things other than UMAP. One thing that I like to do, especially if I have a cross-modal model, like a model that embeds both text and the images into the same space, is to write prompts like, where like chest tube or blurry or whatever, and then put the scores of those prompts on the X and Y axis.
Wow. Okay.
So you can explore anything. But the point, the takeaway here is, yeah, totally. I really like the idea. Take the embeddings of the model itself, not of some external model or something, to explore. And you can totally do that too. I think one of the things that we felt really early on was there was a lot of useful tools on the UI side for exploring data, but they were relatively constrained or quite opinionated with respect to how exactly you do that exploration. And we want it to be like as open-ended as possible, so the data scientists can kind of create whatever visualization they want, but then share it with the clinician or the domain expert. Does that kind of make sense?
Yeah, that makes total sense. I guess just one follow-up question. So does that mean that what we input, like for instance, in this example, you have your data frame to kind of read from your CSV. So that CSV probably needs to be changed to kind of make sure it has the inputs of all that we need to see, or is that something else that I'm missing?
No, that's exactly right. So yeah, here I'm being a little, I'm cheating a little bit. Like this is a shorter piece of code than you would actually need, but I'll asking that you trust me that it's not too much longer. But yeah, exactly right. You would need to basically add the embeddings in as an additional column in the data frame. And so one of the things that is quite exciting about the data frames in Meerkat compared to what you might find with a regular Pandas data frame is that in a Pandas data frame, you can have columns for numbers and text. But if you want to have a column for, say, images, or if you want to have a column for like tensors or embeddings, it's quite tricky. You can kind of put them in there, but it's not particularly efficient. And in Meerkat, you can kind of put anything you want into any of the columns. And there's kind of explicit support for putting embeddings into columns. That is like multidimensional tensors can just be thrown into the column alongside the other metadata that you have. And so the way that this would work is someone would kind of, there might be an additional line of code there that just says like df bracket embeddings equals, and then, whatever code you need to write to put the embeddings into the data frame.
Awesome. Yeah. I mean, I have one follow-up question, but more on the engineering side, but I can save that for later. So
yeah, sure. Or you can also go for it now. We don't have to.
Oh. Okay, sure. Yeah, I can ask it. So the thing with medical data is that like they are really really large images. So it's not like a CFAR 100 where it's like a tiny 32 × 32, but we have like really high resolution images. And one thing that I've found, like even interfacing with data frames like in Pandas, where I completely ignore the image, but just the embeddings, if I have to do this for a really large validation set, it's not very efficient. So wanted to hear your thoughts on like how can, how can this high res thing kind of be, is it easy or is it more efficient in Meerkat to actually get this, or do we need to make sure our validation set is small enough that it can do all this well?
Let me hand this one off to Arjun, because I think that he's probably
these are great questions. So I mean, just like you said, like medical imaging data is just so high res, and here we're showing x-rays, which are, I'd say, the nicer form of medical images and being 2D, right, single slice. Like both of us, none that we work on like multi-dimensional CT and MRI, and like how do you load these in? So we actually kind of interface very nicely with another tool called PyVoxel, which is kind of a backend for I and Rohir, who's in postdoc in the Amy Center, have built for kind of managing a lot of these medical volumes and loading them in lazily or being efficient about the loading. And so when you actually see what's in the gallery, you're not loading all of the images at once, right? You're only loading kind of what you're seeing. And when you kind of index through the gallery, it'll lazily load all of those images in. So you're not going to be loading in, like, if you have a 300,000 like MR data set, you won't load all of it in. You'll only load what you're seeing on the UI side. And then on the engineering side, like let's say if you're trying to get the embeddings, it works the same way. So it's kind of like, imagine you're doing like your torch data loader, right? And it's not, you're not loading everything into memory and then indexing over that. You're lazily loading whenever you're fetching the index. So we kind of port over very gracefully with those kinds of paradigms of like lazy loading and kind of fast loading and things like that. So you're never like holding all of your data in memory at once. So I'll maybe save this demo for later, but you'll get a sneak peek into kind of how we can do this for things like 3D images as well.
Oh, that's awesome. Yeah, that's great to hear. Thank you so much.
Cool. Yeah, awesome. Thanks for the great questions. These are awesome. Okay, cool. Yeah, Arjun, you want to go forward? Okay, yeah. So we were basically saying we want to try to identify subgroups that could point to places where our model is making systematic errors. And after looking through the subgroups that this slice discovery algorithm discovered, the clinician had this hypothesis that perhaps there's a spurious correlation, that in trying to predict pneumothorax, the model was actually relying on the presence of a chest tube to make that prediction, since folks with pneumothorax often have chest tubes in their x-rays. But this is just a hypothesis at this point. Although we've done the slice discovery, we don't know for sure that this slice actually corresponds with this hypothesis that the clinician has. And so in order to be actually sure that there is this degradation in performance, we need to do a little bit of labeling. So in the past, when I kind of had questions about like, okay, is my model underperforming on a particular subgroup? I would usually have to work with a clinician to maybe send over a bunch of files and then have them label them to try to identify, okay, these are the images with the chest tubes, these are the images without a chest tube. And so we wanted to try to make this process a little bit easier. So if we go to the next step, we can kind of demonstrate how with yet another interface, and this is again just a little bit of a few changes in the Python code, we can actually do some labeling and create like nice labeling interfaces that allow clinicians to go through and quickly kind of identify a set of images that correspond to the slice that they're after, in this case, chest tubes. The other thing too is we can also use machine learning to try to assist in this labeling process so we can do it more quickly. So for example, one thing that we could do is use some sort of cross-modal embedding in order to quickly identify good candidates of chest tubes, and then use importance sampling to make sure that our estimate of the error within this slice is unbiased. But you can also just do regular old labeling. And I think it's just a little bit easier to just share a link with a clinician rather than sending over a bunch of data to be labeled manually. The next piece too is that once you have these labels, you can then take them and go back to the training phase of the pipeline and use the labels to maybe kind of reweight the training examples and improve the distributions that we're no longer running into this issue. Cool. Awesome. So in this particular example, with this particular model that we were using for predicting pneumothorax, what we found was actually pretty striking. After we collected labels for which chest x-rays had chest tubes, what we found was that the overall AUROC was 91%, as I mentioned earlier. But the AUROC on the subgroup or slice where folks with pneumothorax did not have a chest tube, but folks without pneumothorax did have a chest tube, was worse than random chance, right? So this is really striking. It suggests that the model is indeed relying on this spurious correlation. So what the doctor can go ahead and do is leave a note in the interface, send that back over to the data scientist and say, hey, this is a slice that we should look at more carefully and potentially take efforts to explicitly mitigate against this error mode when we're doing training next time. Cool. Next slide. Awesome. Cool. And then actually, wait, Arjun, you want to do this or should I chat about this?
Yeah, I can take a stab.
Yeah, you do this.
Yeah, so Sabri kind of gave like a great demonstration of kind of diving into what this model debugging looks like for kind of chest x-rays, right? We found these issues with kind of having chest tubes where we have lower performance in practice, so we need to refine our models. But this was like a very specific example, right, that kind of we dove into. And kind of the thing that we want to emphasize here is that Meerkat really is a platform for being able to wrangle kind of your arbitrary data, right, your unstructured data, and build out these interactive interfaces to really connect the engineers with the domain experts. So one of the things that we're very excited about is like increasing the span of the number of or types of data that we support. So none of that to your question, kind of what happens when medical data is really large, like we actually have kind of built-in support for things like this as well. And we also have nice support for visualizations for things like code or webs, like HTML, large text documents, PDFs, right? And we're really excited about how we can keep extending this to the different kinds of data types that different domains actually have to interact with constantly. So in this particular example, we're looking at kind of, we have loaded a data frame with all of the examples from the BRATS segmentation data set. And so of course, we're not loading in all of the examples, but we have this nice UI where we're only doing some partial or lazy loading. And we get this nice like medical kind of interface, which of course is not built out as well as maybe some of the commercial ones are, but it really gives us a flavor for inspecting our data.
Does Meerkat currently support like gigapixel histopathology images? Because I think that would be they might be challenging because of the images are typically very big and you will need to like zoom in and zoom out in order to examine the different regions.
Definitely. Yeah. So there's a few ways of building this in. And so one is like you load the entire image if you have the memory to do so, which oftentimes we don't have. But there's other processes where, you can, load in kind of particular parts of the image, right? So you load in particular patches. And then when you do the zoom in, you ping the Python backend and you say, fetch me the rest of the image, right? That's like higher resolution for this particular patch. So the nice thing about Meerkat is that there's this very tight kind of system, if you want to configure it, between kind of what the front end actions or events are, so things like zooming in, and what their responses are on the back end. And it's like kind of configurable directly by the builder. So if you had these gigapixel histopathology images, you can kind of show maybe like a 224 by 224 resolution image. And then when you zoom into a particular image, you can tell the backend to give you the patch that's higher resolution for that particular zoomed in area. So that's kind of more to like the flexibility of Meerkat, which is like, how do you build these interfaces, but still be able to run the events or kind of execute the methods that you want to do on the backend for the visualization.
Yeah. Yeah. And just to add on there, I think one thing that Arjun's saying here is that basically what we can visualize in these interfaces is kind of pretty open-ended, because at the end of the day, it's just like, web development on one end that hits a Python backend on the other end. But I think right now we're basically going to be influenced by what folks out there want us to build, right? So if you say, okay, I want to use this with really, really big pathology images, then we'd be really, really excited to work with you to kind of make that work. So currently it's not supported, but we are currently right now trying to figure out what areas would this be really useful for, and then invest engineering resources to make that a reality for those types of data modalities.
Yeah, sounds great. And then follow-up question is, I know you can give labels for like an image. Does it allow like to give like annotation of like a bounding box or like a irregular kind of shape?
Yeah, Sabri, do you want to?
Yeah, sure. So yeah, so I think in these interfaces here, we're not recording any like bounding boxes, but that's something that like we actually are planning to support pretty shortly, because that's really important. And so the analogous thing too would be like in the text case, we might also want to be able to like highlight particular regions of text. So that's kind of all on our roadmap. So that's a great question.
Sounds good. Thanks.
Awesome. Yeah, these are great questions. And I think just to echo what Sabri said, we're really excited about kind of how the community kind of builds with Meerkat and how that will kind of influence kind of the direction that we also take and things that we do moving forward. So beyond the data types, I think one thing that we're also quite excited about with Meerkat is that it really helped you build these custom interfaces. So we had a particular interface or sets of interfaces that we built for kind of this model debugging. But maybe I just want to build a cool interface for a new model that I created. So this is an interface that I built for RoentGen, which is a vision language foundation model for generating chest x-rays. And so here there's kind of many different parts of this UI that I won't dive into too much, but kind of you have your prompts for kind of generating these images. You have parameters that you can do to control how that you generate these images. And then you can also do things like matching in order to kind of find images that you like or don't like. So like in this particular example, we're going to do image guided text, image and text guided generation. So we take an image that we like and we want to add a pacemaker to it. And so these diffusion models kind of show kind of good promise for doing these kinds of text guided queries. And so we can kind of build this directly in our interface. And so on the Python side, right, this is kind of doing the generation and we're able to visualize it in the interface directly. So it's happening in real time. And I think kind of at a higher level, what Meerkat really enables us to do is now that we're thinking about data and models in the same space, and we're able to bring people from diverse expertise to kind of interact over the same platform, we really can control how we use our models in practice. So I mentioned earlier that kind of foundation models are kind of taking the world by storm right now, but one of the big issues is that they're very brittle, and especially domain-specific applications like medicine, we have to be very careful about how we use them, not just because of safety concerns, just generally because they fail quite easily. So what we really want to do is be able to control how we kind of ask these foundation models questions, right? So how we prompt them, and really be able to refine our prompts very quickly. So in this case, we've created this match component, which is doing kind of a text and image level search. So here what we're doing is we're taking a pacemaker, which is some text, we're encoding it, and then we're finding some positive and negative images. So images that I like and images that I don't like, and using that to search over our entire corpus of images. So this is quite exciting because now I can kind of quickly refine what kinds of images I want to see, or what kinds of images I'm really looking for purely by these text and image-based queries. And of course, kind of maybe the model that we're using here is not the best model, but again, this is kind of the power of Meerkat, is that you can kind of easily switch out what your workhorse is under the hood and still be able to build out these expressive interfaces.
Oh, I just had a quick question / comment, Arjun, here.
Yeah.
I think this is amazing that just to make sure I understood this correctly. So are you running the RoentGen in real time and then getting the
email like this needs to record check.
Oh, I think we just got some interference. Yeah, I guess back to what I was saying before. I was asking if you are doing RoentGen in real time, or is it like you have a bunch of things done already and then you're kind of interfacing from that in a static fashion?
Yeah, great question. So kind of what we've done here is we've like mixed in a lot of data. So we took Checkspert data, and then we also have like mimic data. And then we also have like another kind of, when you run this query, we're actually running RoentGen dynamically. So like it's being run and then we're adding that new image into our data frame. And so you can see it in the gallery.
Wow, okay. So it's not a static CSV that you load and then you kind of interface, but you're actually like doing this dynamically. That's amazing.
Exactly, yeah. So yeah, the data frame can grow or shrink. And we anticipate that happens a lot in medicine, where like we may collect new data and we want to kind of, put it back into our training or validation workflow. I think one thing that I was kind of being maybe a little bit cheeky about, but really excited about is that, well, hey, I can use RoentGen to generate a bunch of images that look a particular way. And then I can search in Checkspert for images that look like the images that I like that RoentGen made, right? So because this is all one unified interface, and you can kind of flesh these interfaces out to be as extensive or as basic as you want them to be, you really get control for kind of what you want to show your domain expert and how you enable them to kind of improve or kind of build on their workflow to get the information you're looking for.
And when you say you can, extract images from Checkspert that look like, images from RoentGen, or maybe just, some other static data set, is it like you are programming like the similarity function beforehand, or is it like, I guess I'm just curious about how it works under the hood.
Yeah. So here we're using Clip, which is kind of a multimodal model that encodes both images and text. And so anytime we generate a new image, we're encoding that image with clip. And then so now it's like kind of, it's embeddings cached somewhere, right? So we can go ahead and use them. But that workhorse can be anything. You can imagine even adding a dropdown where you can change the model that you're using for your embeddings, right? So maybe you have embeddings from clip, maybe you have embeddings from convert, which is like X-ray specific. So I think that's, again, like kind of power to the user to configure.
Awesome, thank you.
Yeah. So yeah, I think kind of the takeaway here is that like we really can build out these kind of interfaces that allow us to wrangle over our unstructured data and really bring models, whether they're foundation models or just the models that we typically build, into these interfaces that allow us to reason over large amounts of data.
Cool, awesome, yeah. So I think the last thing we want to say, and I kind of expressed this sentiment earlier, is we're currently at the phase of, we built this tool, we're really, really excited about it, but most importantly, we're excited to sort of work with others to figure out A, where it could be useful, and B, where we should invest more time in terms of developing things out and adding more features, et cetera. So really encourage folks to check out the tool and also download it and try it out on your own data. And then also give us feedback. This is a research project. We're trying to understand how tools like this should be built. So we're really, really interested in hearing about where things work, where things don't work, and how things can be improved. So yeah, thanks so much for listening.
Thank you so much, Arjun, Sabri, and Karan, for the very exciting talk and very interactive. Yeah, everyone feel free to check out Meerkat and provide feedback as much as you can. Yeah, let's open the floor for questions. Oh, before we start, let's all give them a round of virtual applause. Thanks for the amazing presentation. Is there any question from the audience?
I guess I have more questions, but I'll let other people ask if they have any. I guess while people are formulating their questions, I can ask mine. So I had a question about, so this is very exciting and just the sheer flexibility of, like interfacing with different data types and sizes and so on makes it really cool. Do you have any thoughts on whether, like if I want to, like maybe I have a really, really large model where inference, in fact I need a distributed approach, like I need multi GPUs or even on a GPU. Are those things kind of still supported by Meerkat, or do we need to like flesh that problem out independently and then kind of interface it with Meerkat? What would be the suggested approach?
Yeah, that's a great question. So the way that we're currently handling this is we basically will take, if we have a really, really large model, so say it's like a large language model with billions of parameters, and it does actually need to be spread out across multiple GPUs. What we'll do is we're using a library that was actually also developed in our lab by some of our lab mates called Manifest. And this integrates really tightly with Meerkat. And what it allows you to do is just spin up a server on a remote machine with multiple GPUs that you can ping and ask for basically like responses from. And so a lot of times in Meerkat, there's basically two modes that we operate in. One is the model is locally hosted and we're kind of sending the data directly that way. The other mode, which is increasingly common, is that the model lives behind an API. So it can either be that you created that API using a tool like Manifest, or it's also possible that that API is like provided by some, large tech company or whatever, and we're thinking, a lot about these use cases because we expect going forward, more and more models will be behind APIs, which actually in a lot of ways, I think has been great for my workflow, because what I'll do is I'll just have my data kind of locally, and I don't have to worry about having a GPU on the machine I'm working on, and then I can just hit the API endpoints to get the responses back. But yeah, that's how I'm thinking about it. And
do you, like, I guess for medical images, the API thing still hasn't come up yet, so we still have to run a bunch of PHI stuff locally or in large servers that have multi GPUs. Would the workflow still be the same, where you ping where like where you have this multi-GPU server.
Yeah. Yeah, you'd have two options. Like one would be to either run Meerkat on the server where the GPUs live, and that'll work fine. You can just kind of run it and then interact with it, and then yeah, the model is spread across multiple GPUs, but you can interact with it as if it were any other model. And then the other approach would be, again, to use that private server that you have running the model, and then from other machines connect to that server and make requests. So either way would kind of work. But the main point is, I would say we're pretty agnostic to how exactly the model is hosted, while also trying to kind of support as many as possible and make it easy for folks to integrate with whatever models they have. Yeah.
Awesome. Thank you.
I'm just curious how Meerkat support time series data, since there's like a additional time domain, time dimension. So how does it look like UI?
So for the like medical images or like EEG?
Yeah, like EEG kind of time series data, or like even like videos, any type of.
Yes. So EEG's time series support is something we're pretty excited about. I think Karan has done a lot of work in the audio space. I'm generally very excited about general biosignals. So that's something that like we, if folks are excited about, we'd love to kind of build together and integrate into Meerkat. For kind of the videos for the medical images, right? Like you can have 4D images as well, where you have 3D plus time.
Right.
So that's all handled under the hood by Voxel. So Voxel like loads in the data in the right structure, and kind of it's lazily loaded through Meerkat and gets piped over to the UI. And you can kind of look at your video over both space and time. I guess that's more for pretty visualizations, but it really kind of makes a big difference. I mean, I'm sure a lot of us who've worked in the medical imaging space and have tried to, send our DICOMs back and forth and, load them the right way. It can be pretty challenging. And Sabri and I were actually talking about this, is like, if we had tools like this when we were like starting off in our PhD to just, visualize data super easily, yeah, it would have definitely made a pretty big impact on just kind of how fast we were moving. So I guess the TLDR is like visualization is underrated, but super important for a lot of the applications that we work on.
Sounds good. Is there any other question from the audience?
I also really quickly in related to the topic of time series. So yeah, we were hoping to get in a demo with like ECG or EEG. We didn't get it in time. But if you are curious about how time series support might look like, I pasted a link to a tweet that Karan put out yesterday with a demo of how we support audio. So this isn't a medical application in particular, but it kind of gives you a sense of the diversity and the flexibility with respect to like different data modalities and data types. So yeah, I just posted it in the chat in case you're curious.
Yeah, thanks for sharing the link. If there's no more questions, then let's thank Arjun, Sabri, and Karan again for the amazing talk. Yeah, thanks everyone for joining us today. We will upload the recording of the talk to our YouTube channel later, and see you next time. See you same time next week.
Cool.
Thanks,
Thanks so
everyone.
much. Thanks so much for having us.